This is an introduction to highlight the problem or the methods of Simplex. If the linear programming problem has number of variables greater than 2, the suitable and the most widely used method is Simplex method. The Simplex method is an iterative process through which it reaches ultimately to the minimum or maximum value of the objective function. This method is used to solve even very large linear problems. In many industrial applications, a Simplex algorithm is used to solve linear problems with thousands of constraints and variables. So, the difference between graphical methods and Simplex methods. Graphical methods deals only with LP with two decision variables, not more, because each graph contains two axes. For example, vertical axis for x1 and horizontal axis for x2, but it can deal with more than two constraints, while Simplex methods can be used to solve the linear programming problem for two variables or for more than two variables. The main that the Simplex method is based on iterative process, or to improve the process of solution up to the end. Now let us check the procedure or steps for solving linear programming problems, or actually Simplex method. Firstly we have to convert the LPP into the standard form of LPP before the use of Simplex methods. The standard form of the LPP should have the following characteristics. Okay. The first step in the process of solving the LPP using Simplex methods is to convert the LPP into the standard form. Now, what do we mean by the standard form? To convert it from the canonical form to the standard form. What do we mean by the standard form? Standard form refers to addition or subtraction of select variable S in case the constraints type less or equal. Standard form implies to add slack variable. In case of type more or equal, standard form suggests to subtract a slack variable. So if the constraint type less or equal between brackets maximization, so standard form implies to add slack variable. From the other hand, if the constraints are type more or equal between brackets minimization, we have to subtract the slack variable. All the constraints should be expressed as equation by adding slack or surplus and or artificial variables. For the purpose of this method, we will focus only on slack variable. Later on, when we will introduce with two methods, the big M methods or the two phases methods, we will explain what stands behind artificial variables or surplus variable. The right hand side of each constraint, should be made non-negative if it is not. This should be done by multiplying both sides of the resulting constraint by -1. So generally speak, the three result of multiplication each inequalities by -1 will be form the constraint or this inequality from type less or equal to type more or equal, or on the contrary, from type more or equal to less or equal. This constraint should be multiplied by -1. The aim or the goal of multiplication by -1 is to perform the inequality. The objective function should be of the maximization type. The general standard form of the LPP is expressed as follows. Now, as we mentioned before, Simplex method is a form of linear programming technique. It concerns in particular with the problem of maximization, while the rest two methods, big M and two phases method, are concerned with the problem of minimization. Respectively, The general standard form of the LPP is or should be of the maximization, Okay, now let us introduce with the illustration of standard form. So optimize Z equal C1 x1 plus C2 x2 plus dash Cn xn plus 0 s1 plus 0 s2 plus dash 0 sm. This is a general form of standard form. So C1 either the profit of 1 unit of x1, or in case of minimization, the cost of 1 unit of x1. C2 is the cost or profit of 1 unit of x2, up to Cn also is the profit of xn or the cost of 1 unit of xn. So the coefficients C1, C2, Cn are considered either cost or profit of decision variables. Decision variables here x1, x2, xn. The slack variable s1, s2 has zero coefficient. Now let's move to the constraints. A11 x1 plus A12 x2 up to A1j xj plus A1n xn plus s1. So less or equal, more or equal b1. b1 is a resource solution. The second constraint, A21 x1 A22 x2 plus A2j xj A2n xn plus s2 plus or minus. So etc. up to the last constraint, am1 xa1 am2 x2 amj xj amn xn plus sm less or equal, more or equal pm. So A11, as we mentioned before, let us emphasize, is the cost of producing 1 unit of x1. A12 is the cost of producing 1 unit of x2 where? At the first stage or on the machine A. While A21 x1 A21 is the cost of producing 1 unit of X1 at the second stage or on the second machine. Up to AM1. AM1 is the cost of producing 1 unit of X1 at the M machine. See, at the M stage. S1, S2, Sn, Sm are considered as slack variables. Okay. In case of maximization, need to add. In case of minimization, we need to add the slack variable. In case of maximization, we need to subtract. This very simple standard form, the illustration of the standard form. Let's introduce with some remarks and definitions. Slack variables are defined as the non-negative variables which are added in the right hand side of the constraint to convert inequality into an equation. Such variables are added to the original objective function with zero coefficient. Got it? So, slack variables are defined as the non-negative variables which are added in the left hand side of the constraints to convert the inequality less or equal into an equation. Such variables are added to the original objective function with zero coefficient. Two, surplus variables are removed from the left hand side of the constraint to convert the inequality more or equal into an equation. Surplus variables like slack variables carry a zero coefficient in the objective function. These variables also are known as negative slack variable. So the surplus variables is the compensation of negativity of slack variables resulting from the nature of the constraints as maximization. Now, we mentioned before that slack variable should be subtracted if the constraints are more or equal. So, the negativity of a slack variable is unacceptable. To compensate the negativity of a slack variables, we have to add surplus variable. Okay. Artificial variables are also defined as non-negative variables which are added in the left hand side of the constraints to convert equality into the standard form of simplex. Actually, to convert inequality to the standard form of simplex. Now we have introduced three variables: slack variables, surplus variables, artificial variables. Artificial variables, very wide used in the big M methods. Basic solution, BS. For a system of M simultaneous linear equation in n variables where n more than m, a solution obtained by setting n negative n variables equal to 0 and solving for the remaining plus variables is called a basic solution. Such n variables, of course some of them may be 0, are called basic variables, active variables, and remaining n negative m 0 valued variables are called non-basic variables, non-negative, non-active variables. The basic solution is generally used in the problem of transportation or assignment problem. And the condition is set to solve like this problem is n should be more than m. And a solution obtained by getting n negative m variables equal to 0. So we have to adapt n to m in order to get the negativity relation between m and n and m equal to 0. So for a system of m simultaneous linear equation in n variables given n more than m, a solution obtained by getting n negative m variables equal to 0 and solving for the remaining positivity variables is called a basic solution. This is a basic solution. Basic visible solution, BFS. A basic visible solution is a basic solution which all satisfies the non-negativity restrictions, that is all basic variables and non-negative. Basic solutions are of two types. A, non-degenerate BFS. A non-degenerate basic visible solution is a basic visible solution which has exactly m positive xj, j equal 1 to up to m. In other words, all basic m variables are positive and the remaining n negative m variables will be all 0. Number 2, the degenerate PF has basic visible solution is a basic visible solution if one or more basic variables are 0 value. This is a degeneration. Degeneracy is a special cases, as you remember, of special cases of graphical methods. Now, basic visible solution has two types: non-degenerate and degenerate type. So, Simplex standard maximization problem. Let's introduce with the steps of solution. Convert the system of inequality to remove it. Convert the system of inequality to transform it into equation using slack variables. Step 2, set the objective function equal to 0 for standard form of maximization. 3, create a Simplex table, tab and label the active or basic variables. Active variables or basic variables. 4, select the pivot column. This is the column with the most negative number on the left side of the bottom row. If all numbers on the bottom row are non-negative, we are done. Five, select the pivot row, divide each entry in the constant column by the corresponding positive entry in the pivot column. So divide each entry of the constant solution by the corresponding positive entry in the pivot column. The smallest positive ratio indicates the pivot row, exit row actually. So entry column and exit row. Entry column and exit row. Select the pivot, which is the entry in the pivot column and pivot row, the intersection point between the entry variable and the exit variable. The pivot must be positive conditionally. It cannot be 0. And then identify the new active variable. Seven, perform row operations to make the pivot equal to 1 and the remaining element in the pivot column equal to 0. Making the pilot equal to 1 is optional. Repeat the process by identifying the most negative entry on the left side of the last row. Nine. On the left side of the last row is all non-negative. The solution can be found. The value of each row variables or active variables is equal to the rightmost entry in the row. All inactive variables equal to 0. Step 1. Convert the constraints into standard form and make the objective function 0 equation. By converting the constraint into standard form, we mean to add slack variable S1 and S2 respectively. The new form of the constraints are 2x1 plus x2 plus s1 equal 5 and x1 plus 2x2 plus s2 equal 4. Objective function will be z negative 2x1 negative 5x2 equal 0. ما قديم ما جديد البتاع ده
جديدة. أنا لخبطت بينهم بين محل المؤتمرات.
So let us see the following example where how to solve this problem using the simplex method. Given the objective function, maximize z equal to x1 plus 5x2 subject to 2x1 plus x2 less or equal 5, x1 plus 2x2 less or equal 4, x1 x2 more or equal 0. So this LPP consists of 3 components: objective function, constraints, and non-negativity condition. Also it deals with 2 decision variables x1 x2 and 2 phases of manufacturing. This is the primal table. The left column consists of two basic variables and z, s1, s2, z. The upper row consists of non-basic variables x1, x2, s1, s2, and solution. The elements of this primal table, or the element of cells of this primal table, are the coefficients of equation S1 and equation S2 and equation Z. So 2 is a coefficient of x1 on the first constraint, respectively 1 is the coefficient of x2 and 1 is the coefficient of s1, first equation. There is no s2, that the coefficient is 0. Solution equal 5. So if we move to the second constraint, we will find 1 is the coefficient of x1, 2 is the coefficient of x2, there is no s1, so its coefficient equals 0, and the coefficient of s2 equal 1. The solution is 4. In the objective function, the coefficient of x1 is negative 2, the coefficient of x2 is negative 5, there is no s1, s2, and there is no solution. Triple 0. Now x2 is an entry variable because it faces biggest negative value in the low row, in the row of z, equal x2 faces negative 5. That's why it is considered as entry variable. S1 is exit variable because, or pivot row, because it has the least values resulting from the division of column of solution over the column of the entry variable. So when we divide the values of the column of solution on the right side, 5 except 0 and negative values, 5, 4 over 1, 2, the least value of this operation is 4 over 2. 4 over 2 is more than 5 over 1. That's why we considered S2 is the exit row. Now pivot element is 2, intersection point between S2 exit row and x2 entry column. Pivot equation is the result of division of the values of S2 over pivot element. So S2 equal 1, 2, 0, 1, 4, close the bracket, over 2. So the result is 0.5, 1, 0, 0, 0.5 and 2. These values are considered also as the values of x2 on the next table. Now let us check the change in S1 and Z causing by the entrance of x2 as basic variable. How to calculate these changes? Now, copy the values of S1 as given in the primal table. 2, 1, 1, 0, 5. Now, find the results of multiplication of the pivot element of S1 by the pivot equation. The pivot element of S1 is the intersection point between the row of S1 and the entry variable x2. So 1 should be multiplied by 1, 2, 0, 1, 4. These results should be subtracted from the original values of S1. So 2 minus 1, 2, 1 minus 2, negative 1, 1 minus 0, 1, 0 minus 1 is negative 1, 4 minus 5 minus 4 is 1. This is the new S1 in the next table. Let's see the impact on Z. Repeatedly, we are going to copy the values of S of Z as written in the primal table. Z equal negative 2, negative 5, 0, 0, 0. Now, negative minus. Let's multiply the pivot element of Z by the pivot equation. So, negative 5 should be multiplied by 1, 2, 0, 1, 4. And we will get negative 5, negative 10, 0, negative 5, negative 20. The new Z is negative 2, negative negative 5 is 3. Negative 5, negative negative 10 is 5. 0 minus 0 is 0. 0 minus minus 5 is 5. 0 minus minus 20 is 20. So the negative values are disappeared. This is an indication of the finding of the optimal solution. The iterative or the iteration of the solution will stop when the negative values of Z will disappear. So last station is, this is the last table, consists of two basic variables, S1, X2 and Z. The upper row, X1, X2, S1, S2 and solution. Now, by looking at the left column, the left first column, and the right last column. Let's calculate, not calculate actually, to check the values of S1, X2 and Z. S1 equal 1, X2 equal 4, Z equal 20. X2 equal 4, S1 equal 1, Z equal 20. X1 equal 0 because it has no indicators under the column of solution. S2 also equal 0. So the table shows that X1 equals 0. It has no indication in the under the column of solution. X2 equal 4, S1 equal 1, S2 equal 0, Z equal 20. As proof, let's bring from the first earlier slides. The first constraint states that 2x1 plus x2 plus s1 equal 5 as given. Now there is no x1, so 2 times 0 plus x2 equal 4 plus x1 equal 5. 4 plus 1 equal 5. Proved. The next constraint states that x1 plus 2x2 plus s2 equal 4. Let's check it. There is no x1, that means 0. Plus 2x2, x2 equal no. Okay, x2 equal 4 plus s2 equal 0. 0 plus 4 plus 0 equal 4. Z 2x1 plus 5x2 equal 2 times 0 plus 5 times 4. x2 equal 4 equal 20. Proved.